This video is an introduction to the topic of trigonometric identities, and your main objective is to prove trigonometric identities. So that begs the question, well, what is a trigonometric identity? And firstly and foremost, we would have to figure out what the word identity means in a mathematics classroom. An identity is a statement that is true for all values of the variable. For example, we could look at this equation and try to prove that it is true for all values of x. If it is, then we know that that statement, that equation, is an identity. So let's go ahead and show a formal proof of this. What we'll do is we'll take the left-hand side and we're going to split that out and represent it separately from the right-hand side. Now, when proving a trigonometric identity, or any identity for that matter, as you can see, this one has no trigonometry within it. There's no sine, no cosine, no tangents. We begin by working with the more complicated looking side, and in our case, that would most likely be the left-hand side. So the goal is to get one side to begin or resemble in the end the other side. If we go ahead and we expand by multiplying the 6 over both terms, we'll end up with an expansion of 18x plus 6. The nice thing about the answer that we've obtained is that it is identical for both left side and right hand sides. So because of that truth, we can then make a claim that this statement is an identity, that it is true for all values of x. So therefore, we will restate the original problem statement, claiming that it is true based on our proof for all values of x. Okay, so therein is a definition of an identity and what it means to show proof that a statement is an identity. So let's go ahead and look at this in a trigonometric sense. Okay? What we just did is also the same for equations made up of trigonometric expressions. Not all of them happen to be identities. And really that is the goal, is that I'll give you trigonometric statements and your task is to prove that they are true, or rather untrue, for all values of the variable. In order to meet that goal, you have to have a few definitions in your back pocket so that you can pull those out and rely on them as a tool for simplifying complicated looking expressions such that you can make them equal, left side versus right side. Three definitions we have off to the left-hand side. You can see that we have a definition for the sine of theta, that it is y divided by r, where r is the radius. We also have cosine of theta being defined as x over r, and the tangent of theta being defined as y over x. Now, some time ago, you might have seen this development using the unit circle. So what we'll do is we'll just backtrack a little bit, and we're going to define these ratios in that particular context. Our circle doesn't necessarily need to be a circle of unit radius 1, but we'll make it quite general in saying that the radius will simply be denoted as r. So what we'll do is we're going to draw in a right angle triangle into the first quadrant. Size of angle is irrelevant. But what we will take note of is that the distance marked out from the origin, that is to the right angle, will be denoted as x, units of length. And similarly, the vertical distance from the x-axis to a point on the circumference of the circle, let's say it's here, will be denoted as y. Of course, this length here, the longest side in that triangle, is the radius of the circle and the hypotenuse of the right angle triangle. Now, if we look at our right angle trigonometry, those concepts from the past, we can also identify that based on angle theta, which is here, that x is the adjacent side and y is the opposite side length. Of course, r is the hypotenuse. So what we'll do is, using this triangle, we'll simply validate that each of these definitions are true. And they are true. For instance, if we look at the first relationship, sine of theta is the opposite divided by the length of the hypotenuse. According to what we have in our diagram, that would be y over r. Secondly, you can see that the cosine of theta, which we know is defined as the adjacent length divided by the length of the hypotenuse, would be x over r. And last but not least, the tangent of theta is equal to the opposite side divided by the length of the adjacent, which is y over x. So knowing these particular ratios can be used later on to prove identities. And more importantly, these identities, specifically numbers 1 and 2, can then be used to help us to prove another trig identity. Okay. So we'll do a little bit more in this first video, and then there'll be a second part which will address the Pythagorean identity. So in this part of the video, we're going to prove fundamental identities. These are identities that have a lot more importance when it comes to solving what looks more complicated. These fundamental identities are used time and time again to simplify complicated looking expressions so that we can show that the left-hand side of an identity is equal to the right-hand side. Okay, so let's have a look at the first one, where it says that tan theta equals the sine of theta divided by the cosine. In our proof, we will formally begin by dividing the left-hand side out from the right-hand side. We'll then go ahead and work with the more complicated looking side, which would be the right-hand side. What I would like you to remember is that we have already determined expressions to which both the sine and the cosine of theta are equal to. So what we'll do is we'll move forward by substituting these expressions in for both the sine and the cosine of theta. So we'll have y over r divided by x over r. Notice the double line or division bar that's there. That is the style of division bar used when we have a compound fraction, meaning one fraction divided by another. Coming back to the top right, what happens when dividing by a fraction, as you well know, is that we multiply by the reciprocal. So the reciprocal of that second fraction is r over x. Using our knowledge of rational expressions, we can see that in lowest terms, r over r is 1 over 1, and we're left with y over x. Now going back to the other side, tan theta, we already defined as y over x. Now, lo and behold, we do have a left-hand side that is equal to the right-hand side. So we'll make a conclusion. What we will say is that since, it's an upside down therefore sign, so since the left-hand side equals the right-hand side, this statement, which we will restate, tan of theta is equal to the sine of theta. So it is now an identity. Now that we say that it is true for all values of the variable, so for all theta. Okay? So in the second part, which I would have you watch also this evening, we'll focus on the second identity here, which is the Pythagorean identity.